Hello everyone, I welcome you all. Now I am going to explain thermal conductivity of insulating material experiment in our heat transfer laboratory. The main aim of this experiment is to find out the thermal conductivity of given insulating material by using the concentric sphere method. Come to the description of the operators. This one is the concentric sphere and insulating powder, that means chalk powder, is filled inside and outside sphere. I am going to calculate, we are going to calculate the thermal conductivity of that chalk powder, and 6 thermocouples are placed on the surface of the outer sphere to monitor the temperature readings at various places, and inside sphere is filled with the SAE 40 oil, and one coil, heater coil is directly dipped into that oil to give the heat input to the experiment, and one thermocouple sensor is placed on the surface of the inside sphere to monitor the temperature values of that oil and the surface of the inside sphere. And remaining operators, this one is the console, heater switch, dimmer stat, watt meter and thermostat, temperature indicator and the channel selector. So let us go for the experimental procedure. Here I am giving the power supply to the equipment, switch on the mains, console switch on and heater switch on. By using this thermostat, adjust the voltmeter voltage values by using this thermostat, and by using this heater controller give the some amount of the power, and after that check the temperature indicator values by using the channel selector. In this channel selector, T1 indicates that, T1, T2, T3 indicates that upper surface temperatures of the outer sphere, and T4, T5, T6 indicates that lower surface temperatures of the outside sphere, and T1, T7 indicates the oil temperature. So by using this temperature indicator and the channel selector, monitor the temperature values at various positions. Observe here, the temperature values are changing with time. So the system is in unsteady state condition. Wait for some time till the system reaches to the steady state condition. After reaching the steady state condition, tabulate the values of wattmeter readings and temperature reading. Wattmeter readings, that is 50 watts, and after that note down the temperature readings by using this channel selector, and T2, T3, T4, T5, T6 and T7. After tabulating the values of heat input and temperature values, go for the experimental calculations. These are the values obtained during the experimentation. Initially the values are like this, and after the 10 minutes the values are varied like this, and after the 10 minutes the values are varied like this, and after the 10 minutes the values are varied like this, and after the 10 minutes the variation is very low. So we considered this is the steady state and going to calculate the thermal conductivity for these values. And this is the block diagram of the concentric sphere, and this one is the inner sphere surface, and this one is the outer sphere surface, and this is the insulating material provided, that one. So here we considered this concentric sphere as the plane wall, and K is the thermal conductivity of the plane wall, and thickness of the wall is the R2 minus R1, and outer surface temperature is the T0, and Ti is the inner surface temperature. So apply Fourier law of heat conduction. Q equal to Ka into dt by dx. So K into A into dt means temperature difference, that is inside temperature and outside temperature difference. Here I am writing Ti minus T naught, because here heat is flowing from inside to the outside. Ti is the higher temperature and T naught is the lower temperature, and dx is the thickness of the wall. Thickness of the wall is the R2 minus R1, and here we need to substitute the logarithmic mean area, because here we considered the concentric sphere as the plane wall. That's why we need to substitute the logarithmic mean area. So logarithmic mean area of the composite sphere is 4 pi r1 r2 Ti minus T naught divided by R2 minus R1. In this formula, Q means heat input to the equipment. This directly came from the table, and K means thermal conductivity. We need to calculate the thermal conductivity, and R1 R2 are the inside and outside radius, inside sphere radius and outside sphere radius. Here R1 means 75 mm, and convert this into meters. 0.075 meters, and R2 radius of outer sphere, that is 100 mm, convert this into meters. 0.1 meters, and Ti means inside surface temperature of the sphere. This directly came from the table, and T naught we need to find out the surface temperature of outside sphere, because 6 thermocouples are placed at various places of the outside sphere. So we need to find out, and our T3 plus T4 plus T5 plus T6 divided by 6. Substitute the values. 39.8 plus 39.8 plus 39.9 plus 40.0 plus 40.2 divided by 40.2 plus 40.0 divided by 6. Calculate this one by using the calculator. Outer surface temperature is 40.2 degrees centigrade, and Ti equal to T7, that is 52.7 degree centigrade. So substitute all these values, that is T naught value, Ti value, radius values, thermal conductivity, heat input values. All these values substitute in this equation, we will get the thermal conductivity value. K equal to Q into R2 minus R1 divided by 4 pi R1 R2 into Ti minus T naught. Substitute the values here. Q means 50, whatever the input is given to the system, and R2 means 0.1 minus 0.075 divided by 4 pi. R1 means 0.1, 0.075 temperature difference, that is inside temperature 52.7 minus 40.2. Calculate this value by using the calculator. So 1.06 watt per meter degree centigrade. Finally, thermal conductivity of insulating material value is obtained by using the sphere in sphere method or concentric sphere method, as thermal conductivity equal to 1.06 watt per meter degree centigrade. Thank you.